Yes, thank you. Yes, so we saw this morning the UOV construction. Okay, then we saw the MPC in the head construction as well. I'm not going to talk about analysis on that one. It's mostly, so I'm going to focus on actually solving the MQ problem, which is very relevant for anything, any area that you want to work with in crypto. So either it is code-based or multivariate most of the time. I'm going to talk about algebraic cryptanalysis. So this is not a synonym with multivariate, even though actually we sometimes look at it this way. You can use it to analyze multivariate crypto, but you can also use it in code-based crypto, for instance, and so on. So the first part is going to be mostly about how we solve systems of equations. So the second part is going to be application of this to UOB. Okay, so yes, we can see the slides. Okay. So as I said, algebraic cryptanalysis, that's going to be the first half, well, more than half of the talk. That is a type of cryptanalysis where you reduce the problem of attacking your system into the problem of solving multivariate polynomial systems of equations. Okay, so you look at the description, you look at the construction like we did this morning, and you think, what can I infer from this? What do I know about this system? And then you try to model this as polynomials. So we're going to see examples of how this works. This is the workflow, usually. So you start with, as I said, you start with a cryptographic scheme that you want to attack. And here I put multivariate signature scheme. That's what we're going to see today. And then you have some other data, right? You have a public key and or you have a message. Let's say I will focus on signatures now. So our goal is going to be either to find the private key and be able to sign anything, or it's going to be to forge a signature for a given message. So that is the data that you start with. And then you take this and you do the algebraic modeling. You see, yeah. You model first your attack, so you get a system, an algebraic system, and then you give it to an MQ solver, so a solver that is able to solve systems of equations, usually in an exponential running time, but still. And then from the solution that you get from the solver, it's going to be like a pre-image of, it's going to be a solution of your system, but that is also going to correspond to either the secret key or to a forgery, to a forged signature, depending on what your attack goal was. Okay, and so first, as I said, we're going to cover the solving part. So I'm going to talk about some state-of-the-art solvers for this. And then in the next part, we're going to apply this to actually to UOV. So I'm going to show you generic attacks on UOV. So not those that are specific to the various structured systems that we mentioned this morning, like SNOVA, Q, R, UOV, and so on. These are the generic ones, so attacks on UOV. And of course, what I mean by attacks here, it's like the state-of-the-art of how well we can do, right? They are not, the parameters are already adapted for these attacks, right? These are the baseline of how you define parameters for UOV. Well, the last one is going to be. Okay, so let's recall from this morning, we had this MQ problem, right? I told you you are given M multivariate polynomials in n variables, and then your goal is to find an assignment of all variables, or said differently, you need to find a tuple such that all of the polynomials vanish on this. And then here is an example. This is over F2. We're going to look at examples over F2 in the beginning, right? So this is a concrete system. And I'm going to do this overview of different ways that you can solve this. And the way that this diagram shows the different solvers is going from, I don't know if you can see very well with the light, going from those that are very well adapted for systems over small fields. So starting from F2, and then when you go up, those are all very much better performing for bigger finite fields. What is the big intuition here? Well, here there's a lot of enumeration, so of course, yeah, this helps sometimes, but it only helps if you're over small fields. If you're over a big field, you don't want to do any enumeration, so you go into Grosvenor basis. So we're going to cover those. I'm going to start here. And then I'm going to go on the other side, right, tell you about the Grosvenor basis. And then if we have time, we're going to finish with the crossbred. Let's say that is in the middle. Okay, so first, as I said, enumeration. So what is that? Exhaustive search. And this one is actually fast exhaustive search. It refers to an actual library that does enumeration in a very, very fast way. And it is actually very hard to beat in practice. Well, we do have algorithms, but it is not easy to beat exhaustive search even. Okay, So this is basically how it works. You're building the binary search tree, right? You're doing a depth-first traversal of the binary search tree. So what I mean by this is like if at the root here, the first, let's say this level corresponds to setting the first variable in this example, x1 to either 0 or 1, depending on where you branch, right? So here I set x1 to 0, and then I look at the equations. Well, I don't look at the equations yet because we're going to enumerate everything, okay? So first you set everything to 0, right? And then you check your equations and you see whether, okay, is this a solution or not? And then so you see here because of, the second equation, it doesn't really hold. You're getting something that is 1 equals 0, so you have an inconsistency. So you know that 0, 0, 0, 0 is not a solution to your system. Okay, then you backtrack. Where do you backtrack to, let's say, the last, then you go to the next value, let's say. So here I'm just going to change the value of this, the last variable. Maybe that is the one that created the inconsistency, still no, and so on. And then you continue, okay, you're doing the depth-first traversal as you do. And at some point, and so every time you just check the equations, and this is an example that brings us far, and at some point you see that, okay, here I found a solution, a branching where all of the equations are equal to 0. So it was the branching x1, 1, and then x2, 0, 0, and then again 1. Okay, so we found the solution by just brute forcing it. Okay, why am I starting from this? It's gonna, all of the other techniques kind of build up on this. This is the core of how you solve non-deterministic problems. Okay, so worst case complexity, right? If at worst, I will just enumerate everything. If the solution here was 1, 1, 1, 1, I go through all of it. So it is 2 to the n, where n is the number of variables. And if you want to generalize this over FQ, of course you can. You're going to make a ternary tree, a quaternary. Usually you don't. Yeah, we brute force over F2. Okay, now the library that implements exhaustive search, it doesn't do it in this way, actually. It does a bit of a more intelligent, let's say, exhaustive search, and that is it enumerates not in the order of the order that you would get with a depth-first traversal, but it enumerates in the order of a gray code. And here, you don't see the title, but that is a gray code. So it is an ordering of the binary system where every time you go from one element to the other, you just flip one bit. Okay, so here we flip the first one, then we flip the second one, and we get a 3 instead of a 2, and so on. Okay, so why is this interesting for enumeration? Well, because if you look at what I'm doing here, here I enumerated the 0, right? I'm trying first with the 0, and it doesn't work out. So now I'm just going to flip one bit, and so just the last branch is going to come here. And 0, 0, 0, 1 was not a solution either. So now my next thing that I need to check is the 0, 0, 1, 1 vector, right? So if I want to represent flipping only one bit here so that you don't change everything in your equations, you need to take the whole branch, right? So you're just moving on this side. And you see I didn't move the fourth assignment, just the third one. Then, again, you switch the first one, and then again here I'm going from 0, 0, 1, 0, and then I want to flip the third bit, so then you just need to take the whole branch, and this is the corresponding one, and so on and so on, and eventually, I think this is, again, an unlucky example. We're going to find it even worse than with brute force, but that is just depends on your instance, of course. Yep, it was here. Then you find the solution. Okay, so this library does this implementation and many other implementation optimizations. Still, the worst case complexity is 2 to the n, but it differs from the depth-first traversal in polynomial factors. Even you can even argue that it differs even asymptotically. That one is hard to beat in practice over F2 up until, I don't know, 30, 40 variables, it's hard to beat. Okay, so then after this, what can you do a little bit more intelligent than a brute force, right? You can do, instead of doing a full enumeration, you can do partial enumeration and look at your system and see whether you find some inconsistencies or not. Okay, and this is at the base of SAT solvers. So I'm going to tell you just briefly what SAT solvers are. I'm not going to go into too many details, but it is... this is where it all comes from, so yeah, we have to say it. So SAT solvers solve this logical normal forms, okay, so conjunctive normal form. Instead of looking at systems, algebraic systems, you have only logical operators, right? So one, let's say now instead of an equation, it's going to be, it's called a clause, and then a clause is a disjunction of literals, so the or. And then you put several disjunctions, you put them in sequence, and you put an and between them, and that is the type of logical formulas that SAT solvers can read. Okay, and when you solve them, it's using this algorithm. So, and you have the satisfiability problem. That is a very core problem in computational complexity. Okay. So, what do we do in SAT solvers? And also, we use techniques like this in algebraic cryptanalysis as well. So, when you do partial assignments, you're not just going to assign everything. You're going to assign the first variable, let's say. And then you look at your system and you see whether, okay, these, do I know something more now by setting x1 to 0? So you can see that you might still have a solution, right? It is not inconsistent, so you have to go further in depth, right? You have to make some more guesses, which adds to the complexity. And then you set x2 to 0, and then here something happened, right? I think because of, one of the equations doesn't work out, and I think, I forgot which one it is now. You can take a look. The second one again? Yeah, it makes sense because that was the branch. Yes, so you see immediately, even without setting x3 and x4, you see immediately that, this is not a possible branching solution. So here you stop, you backtrack immediately. Okay, and so you unset x1, you set x2, and then again you find an inconsistency. So you backtrack again and so on. And here in this branch, I think, yes, you can also propagate and find the solution immediately. The way that you, so what you do when you assign things, you first see whether you can propagate something, right? What I mean by propagation is that you can infer the assignment of another variable by, looking at the system. Or you can discover conflicts like we did on the left. You can see that there is inconsistencies. Okay, so this helps the complexity. Why? Because here you see I skipped a lot of the branching. Everything that is here doesn't contribute to the complexity. Everything that is propagated also doesn't contribute, right? Because you're going directly deterministically down instead of branching out. But still, in terms of worst case complexity, we don't know, right? It depends on your instance, so it is the same. Worst case complexity, which portion of the branches are missing, right? That is going to tell you, the number of leaves is going to tell you the complexity, but actually in general, we don't know. It is still, in the worst case, it is still 2 to the n. Okay, but that is the idea of partial assignment and conflict search. And that is SAT solvers, and I put here, it is, again, 2 to the n. Okay. Something better than you can do, and this is at the basis of both a SAT solver that we made, and also then we turned it into an algebraic solver, which was a lot faster, yes, I need to go down now. In order to tell you these techniques, I need to tell you some notions that will be also important later for the Grosvenor basis and so on. We're going to talk about linearization. Okay, so we're going to first see what is what we call a Macaulay matrix for a given system. When I said linearization, so we started the talk this morning also by getting this intuition that, okay, linear systems are easy to solve, right? Non-linear systems are hard. So first solution, what if I just linearize everything? What I mean by linearization, that every time I find a monomial that is not linear, I'm just going to substitute it with a new variable. Okay, so I'm adding a variable, and then that is and I'm going to replace all occurrences of this new variable by the same one. So for instance, here I have x1 times x2, and I plugged in y1 instead, okay, and then I substituted all occurrences, okay. And now you see on the right here, we are faced with a completely linear system, okay, so good. What's the catch? Right? If we have a linear system, we said it is easy, right? Why can't we solve all quadratic systems? So when you're adding these variables, right, you are basically, your system is still consistent, the solution will be there, but you're going to add more solutions, right? Because you have some loss of information by changing this variable. Okay, first, intuitively, if you look at your system from a linear algebra point of view, you know that a random quadratic system of m equations in n variables, it should have around 1 over q, it should have about one solution. I'm not gonna go into details of this, but yeah, we are going to use it. So yeah, the intuition of linear systems kind of transfers, not completely, but yeah, if you have the same number of variables and solutions, you should have about one solution. Or in the homogeneous case, q solutions, of course. And if you look at the corresponding linearized system that we got, well, how many solutions does that one have? I have one variable per, one variable per monomial, so that is n plus 1 choose 2, right? And then if, and you add also the linear monomials. So if you look at, so that is the number of variables, right? And if you look at the number of equations, the number of equations is still m, it is very small. So you get a solution, or you get a solution space of this dimension, which is very large, okay? And it makes sense because you lost a lot of information by doing this, right? For example, your system doesn't know anymore that x1 times x2 is the same thing as y1, so you can have inconsistencies like this, right? This, for instance, might be also a valid solution to your system, x1 set to 1, x2 set to 0, y1 set to 1. But you don't satisfy this nonlinear constraint, okay? So that is why this doesn't work immediately, but it is still a pathway to what we're gonna do next. Okay, so what is the Mokalei matrix? It is, I'm going to fill it in with this linearized system, right? So here is the example that we had, and I'm gonna put in the columns, it's going to be all of the monomials, right? And then in the row, it's going to be all of the equations, and then I'm just gonna fill in with the coefficients, right? And here it's going to be zeros and ones. So for instance, here, for F1, I have for x1, x2, I'm gonna put a 0, right? Because it's not there. Then I'm gonna put a 1 here, right? Then a 0 again, and so on. You see how we fill it in? Yeah, so you fill it in with the coefficients of the linearized variables. Okay. So now that you know what that is, I can go into the techniques of this simple algorithm. It does exactly what a SAT solver does, right? So you do some partial assignment, and then you do Gaussian elimination, and then you see what will happen. Yeah, the simple idea, I guess sufficiently many variables so that the remaining polynomial system can be solved by linearization. What I mean by this? Okay, so when do you expect to be able to solve everything by linearization? You want to have one solution, right? The problem was that we had a huge solution space. We had a solution space of a big dimension, right? So you want to have as many variables as equations. So that means you have to have as many monomials as equations so that the linearized system works out, okay? So you enumerate until you get to a square matrix, until your Mokalei matrix is a square, and then you should have a unique solution. Very simple, actually, for generic systems, it's not so bad, and the complexity, finding the complexity of this is a very simple matter, and this is going to be the last solver that I tell you about where this is going to be the case, okay? So then for everything else, finding the complexity of solving, it's going to be different. So what is the complexity here? If n is my number of variables, m my number of equations, okay? So enumeration ends, as I said, when the number of monomials is smaller than the number of equations, right, or equal. Okay, so that corresponds to, we want the number of monomials is, this is the number of monomials, right? The remaining variables choose 2. And so how many do we need to enumerate here? Well, it is exactly this. We need to enumerate n minus a square root of 2 times m. Okay. And now there is a quantum version of this algorithm for system solving because of the simplicity, exactly, right? It is not better than the attacks that I'm going to show you, the algorithms that I'm going to show you next, like the crossbreed, but it's interesting for its simplicity. Okay, so now I'm going to go on the other side. As I said, I will stop here with the crossbreed. So that was for everything over small fields, right? You want to do more enumeration because it pays off. When you go over big finite fields, you want to go more to Grobner basis algorithms. Okay, And I'm going to give you just an intuition on how all of these Grosvenor basis algorithms work, specifically for the case of solving systems of equations, okay? Not for finding a Grosvenor basis or membership testing and so on. I'm going to focus on the case of solving systems of equations. And basically what I'm going to show you is we are describing the XL algorithm, actually. Okay, so we start again with the Mokalle matrix. At degree 2, right? You linearized your system. And as I said before, you want, when do you win? When you have a square Mokalle matrix. So what we did before is that we enumerated a variable. So we were trying to have fewer columns in the matrix. That's how we got into a square matrix, right? What is one more thing that you can do? You can try to have more rows, right? How do I find more rows? That is, I need more constraints, right? That is not, it's not necessarily something that we can do. However, we can do it in the linearized case. So for instance, I can add something like, x, this is again our, let's say, our system. So if I want to add another equation, what can I add? Where I know also that if f1 is equal to 0, then x1 times f1 is also equal to 0, right? That is something that you know. Or multiplied with any variable is still going to be 0. Okay, so those are new equations that you have, right? So you can add those equations. They are algebraically dependent to the other equations, but here we are looking at the linearized system, right? So they are not, they won't be linearly dependent to the rest. Okay, so you can add this. And in your linear system, it will look like a new equation. And then you can do this with for each equation, for each variable. You go to degree 3 and so on. So what's the catch again here, right? It would be easy if we can just produce variables like that, equations like this. The catch is that when you multiply x1 times f1, the degree of your system goes up as well, right? You get a degree 3 system. So you don't only add equations, you are also adding monomials, like you see here on the right. So this is called augmentation in Grosvenor basis attacks. Right? I'm adding here these equations, and then I need to add also the new monomials that will appear. And you can also do this to degree 4 and so on. You can go up. How far do you go up? Well, if you look at the complexity analysis, so the theory tells you that if at some point when you get to some degree, you will end up with a system that has more equations than monomials. Okay, if you continue doing this, you will reach a point where you get this square matrix. Okay, and that is when you need to solve this huge system, linear system, and then you get a solution. Okay, so what does this correspond to? I just want to tell you an intuition on what a Grosvenor basis is. For this, I'm just, I'm going to remind you what we're doing if you want to link it to, the theory. So we are working, over a polynomial ring, right, in n variables, and then we are actually building, we are enumerating the ideal of this, we are enumerating an ideal of this ring, which is the ideal generated by these equations that we have in the beginning, right? So let's say you have this set of generators, and then you know that, you know by the Hilbert basis theorem that if any, any ideal in R has a finite set of generators. So let's say for you it is, this one. And then, okay, so if I mention sometimes an algebraic variety, this is going to be it. So it is all of the, basically it's the solution space, right? But the algebraic space. So all of the assignment of these n variables such that all polynomials vanish on this. And then, why did I want to tell you this? Okay, we don't have to go into the details of this. So my point is that if you start from a given set of generators, this is not a unique generating set of your system. You can also transform it, right? You can do some algebraic transformations like we did when we were coming up with new monomials, right? Or with new equations. When we were multiplying one variable times a polynomial, then you are finding new elements of your ideal, you're enumerating it, and then when you're doing this Gaussian elimination, you're kind of removing those that are repeating, so you still are kept with some generating set. And then a Grobner basis is just, it's a set of generators with some nice properties. Okay, so the set that we started with is not necessarily nice. You cannot really solve the system starting with this. What is a nice property depends on what your goal is for this, for when you're computing a Grobner basis. For us, the goal is what? Is to solve the system, right? So we want to have some description of our system or a generating set that makes it very easy to infer, to find the whole variety. And this happens. Actually, I'm going to show you what the shape of this Grobner basis is, let's say in lexicographic order. So for instance, the system that we started with, if you look at it like this, we have no idea what the solutions are. But if I compute the Grobner basis of this is what the Grobner basis looks like. Okay, so it has this very nice shape that allows you to enumerate the solutions immediately. Usually it's because you have, at the end you have equations with very few variables, only one, right? And then in the next one, there's going to be two, and so on and so on. So what is the solution of this? Can you, like, just looking at the system, you can find solutions now? Once I gave you the Grobner basis. You start iterating from the bottom, right? You have x5 is equal to 0. So that is definitely, it's, even just from this equation, you can infer already the value of x5, right? Then from f4, there you have to make a guess either on x4 or x6, right? Yeah, maybe, or it can also be the other way around. Sorry? Ah, yes, okay. So when you make a guess on x4, this is going to give you the value of x6. Then when you make the other guess, this is going to give you another value for x6, and then all of the rest is deterministic, actually. So yeah, those are the two solutions. Ah, wait, okay. So there's two solutions to the system. I don't know why they don't appear. Yeah, setting x4 to 0 will give you one, and setting x4 to 1 will give you another solution, and that's the whole variety. It was supposed to be on the slides. Okay, and then the things that, yeah, if we want to go into the actual different algorithms for Grobner basis, these are all the things that I didn't talk about, so monomial orderings, like how you, when you are building this, when you're augmenting the system, I just told you the XL, which is like for each, right? For each variable, for each equation. You can do this in a smarter way by avoiding, when you're creating a new equation, it might be either a new linearly independent equation, or it's going to be one that is linearly dependent to the others. And those you want to avoid because when they don't add anything to your resolution. Those are called syzygies, for instance. So you might want to try to find criteria to not compute those. So everything around that is in these different algorithms, these F4, F5 algorithms, and so on, that we're not going to talk about. But you have the main intuition now of how Grobner basis algorithms work. And we can also know about the complexity now, okay? It is a bit more complicated. What is the more complicated thing here? What would be the complexity? So what did we do? We augmented, then we solved a huge system, right? And so the bottleneck actually is going to be to solve this huge system that you obtain in the end, okay? So it is a bit counterintuitive, but yes, the Gaussian elimination that you do is the bottleneck of this algorithm. And then to know what the complexity is, well, you need to know how far you go with the degree, right? I told you that at some point you will stop augmenting at some degree, but what is that degree? So that is the thing that you are missing. Okay, and okay, I'm gonna call this degree, let's say D-reg, right? Because we call it the degree of regularity. So then the complexity will be what? Literally solving this huge matrix. This huge matrix is going to have how many variables? N plus this is the number of monomials that you have at that degree. And so this is the size of the matrix, and this omega here is the linear algebra constant, okay? So yeah, Gaussian elimination, it's either to the third if you do it naively, or if you do better algorithms, it's 2.7, or if you have sparse systems, you can go lower, so that is this constant there, this omega. Okay, and then times something for building the system and so on. We still don't know what the complexity is, right? This D-reg, how big is this D-reg? And so that one is given by this Hilbert series. So you expand this series, actually. And then when you find the first non-positive coefficient in this expansion, that is where your that corresponds to the degree when your algorithm stops. So actually this series, if you expand it for each coefficient, it will give you the number of monomials minus the number of equations. Okay, that is what it models. It gives you the number of monomials that you have at that degree minus the number of equations that you can expect at that degree. So when this goes into minus, well, it can never go in minus, but yeah. When this gets to 0, it means you have more equations than monomials. So that is when you win, actually. Okay, so this is how we find the complexity. This is for generic systems, right? So if your system has additional structure, you cannot predict. Here we are mostly counting, let's say, the number of monomials, and then we are counting the number of equations by taking into account these reductions to 0 that will appear starting from degree 4 and so on. So if you have a very random system, usually it will follow this, right? Otherwise, yeah, we have no idea what the complexity is going to be. Okay, so, but I put it there because here we are solving, let's say, generic systems. Okay. Do we have questions on that? No? Okay, so then these other algorithms, yeah, there is a FXL, hybrid, bool solve, they're all in the state of the art. I'm going to tell you about them in the summary because here, the way that I set up the talk is I'm telling you only about the techniques that exist in each algorithm, right? And then in the summary, I'm going to tell you which algorithm uses what and so on so that you have like a big overview of everything. They involve techniques that we already talked about. One thing that we didn't talk about is techniques in this crossbred algorithm, so the one in the middle. That one has some additional techniques. It's also an algorithm that is very good for small fields, so only implemented for F2 for the moment, and but it is a record setter for F2. So we're going to see some other ideas that appear there. So what is happening in this crossbred algorithm? First, we're going to, let's say this is the Macaulay matrix. If you noticed, I ordered it a bit differently. I mean, the columns, they are in Gravelex ordering because this is going to be good for what we want to do. So first, what you do is you put the matrix in reduced row echelon form like this. And then, for instance, if we had another 4 equations, which, what am I telling you about here? Yeah, I want to tell you about this one first. So this technique is, why did I order it in this order? So if you put it in row echelon form, here, for instance, this x1, x2 doesn't appear anywhere else, right? Because it is a pivot now. Same for this one, and so on. So if you look at if you look at this subsystem that I'm taking here, right, that is highlighted, it is linear in everything but x4. For instance, if you enumerate x4, then you get a linear system. Okay. So this is another optimization. You can put your system in this form. You can take a subsystem, and then you have fewer enumerations. So you enumerate the one variable, and then you solve like a linear subsystem. And this gives a better trade-off than just enumerating anything. Or, on the other hand, I could have chosen not to enumerate x4, but to, let's say, linearize the system that is left, right? Here I still have x1 times x4, x2 times x4, x3 times x4. I can still linearize it and then solve that one. If I have enough equations, then that's also going to work. And what is the first thing that yes, okay, this is just an intuition for the next one. Yes, you can do, put it in row echelon form and just take the last part that contains only linear monomials, yeah, technically. If you have enough equations, that will solve the problem immediately, but this usually never happens in practice, yeah, you have to do some enumeration. Okay. So those are kind of like different tricks that you can do, and this algorithm is very well performing, but it's very complicated to analyze the complexity because we have different parameters now, right? What gives you the complexity is you have an optimal choice of these parameters, like how many am I how many variables am I leaving non-enumerated, how big of a degree I go to, and so on. So these are the different, let's say, parameters of the complexity. For instance, yeah, you can decide in the beginning to enumerate age variables. This for parallelization doesn't matter that much. These other three parameters are important. So let's say k is the number of remaining variables. So for instance, here we chose to enumerate only 4, or the x4, right? So the number of remaining variables will be 3, let's say. And then you chose to augment the system up to some degree, right? To degree 3, 4. In practice, it's only up to degree 4. Otherwise, if you calculate the memory for this, yeah, it doesn't to go up to F5. From a very modest number of variables, it doesn't fit in the whole memory in the world. And then, okay, so you choose how many variables are going to remain, you choose up to which degree you're going to go, and then you're going to compute this. So you compute the Macaulay matrix up to this degree D, and then you take the subsystem, like we saw, you take a subsystem that is at most a degree linear for us. What we saw was at most linear, but it can be, you can also decide to linearize, right? That was the third here. You can also choose to linearize, so the d can be bigger than 1. That is what the small d refers to. And then you enumerate all but the k chosen variables, and you get a linear subsystem, and then you find solutions to this subsystem. And then you check whether your solutions are consistent with the rest of the system. It's like a high overview of how this algorithm works. And then the complexity, yeah, as I told you, it is the best trade-off between these 4 parameters. Well, 3 parameters, let's say. And that is, I will not give you a formula for that. There is no formula. There is just a script. Even admissible parameters, just meaning that the algorithm will finish, that is also not an easy thing. Okay, but it is a record setter. So here I didn't update it, actually. This is from the Fukuoka MQ challenge. So it is, yeah, they had a project where they set up several instances of the MQ problem, so that people can work on algebraic solvers and try to solve them and so on. And here for this kind of systems over F2 and where we have determined systems or over-determined systems, right? I didn't talk about what happens when you have more variables than equations. Here we have an implementation of the crossbred algorithm. So the best that we can do is 83 variables. And this is in twice as many equations, 166. And then even before that, previously, the record was at 74. So with the introduction of this Excel crossbred algorithm, and also, yeah, a parallel GPU implementation of that, and so on. And before that, it was this libfes, the great code enumeration stuff. Okay. And I'm going to leave the complexity like this, of course. Okay. So now a summary. As I told you, we set up, yeah, the techniques on the top. And then on the bottom, I have the different algorithms that I was mentioning. So I'll just do like a quick summary of which algorithm uses what technique. So fast exhaustive search, that is that was this binary search tree, if you remember, right? Enumerating everything. And that no, here, sorry, I'm reminding you what the techniques are. So partial enumeration was this binary search tree, right? And then candidate solutions, what was candidate solutions? If you take a subsystem instead of the entire system, and you still have some more solutions, but you can, you have a solution space of a small dimension, not necessarily 0. So then you can still check against the rest of the system for each solution that you found, and this is sometimes better than doing something else. So that was the candidate solutions technique. Then you had the conflict search, right? Conflict search was SAT-based, right? You do some partial assignment, and then you see whether your system is still consistent or not with this choice of guesses. Extending to higher degrees, that is the augmentation of the Macaulay matrix. And then we had computing a Grobner basis, yeah, which is not necessarily a technique, but yeah. So libfes does only enumeration. That is the one technique that it has, and everything is a very good implementation choice. SAT solvers, they do partial enumeration with conflict search, right? So what we described is this DPLL algorithm where you do propagations and conflict search when you choose something. And then we had this simple solver is the same thing, as I said, as the SAT solvers, enumeration and conflict search, but also at the implementation level, it's a bit more involved than that. We also use these candidate solutions and subsystems. Then FXL, what is FXL? So it is the algorithm XL that I told you about, but a bit in hybrid mode, meaning that before you start doing this algorithm, it might be a good trade-off to first do some enumeration of your variables, right? You enumerate some variables, and this actually lowers the complexity very, very quickly because for these algorithms, like, I don't know if we saw enough for you to have that intuition, but the more disbalanced it is in terms of equations versus variables, what I mean by this is, the hardest case is n equals m, right? Once you get one more equation, another more equation, the complexity goes down pretty quickly. Okay, so sometimes it is a very good idea to enumerate some of the variables because then you immediately, you get fewer variables, so the number of equations is a lot bigger and then the complexity is better. So that's what FXL does. First some enumeration and then extending to higher degrees, like we saw. Whether it computes a Grosvenor basis or not, I don't know, it depends on how you instantiate it. In the original paper, it doesn't say. You don't need to compute a Grosvenor basis, I would say, but depends on how you implement this. And then a hybrid algorithm is, this one, the hybrid one actually computes a Grosvenor basis. So first it does some partial enumeration and then it does this full Grosvenor basis computation. This bool solve that used to be a record setter, I mean, not practically, but that used to be a state of the art for a while. It is also like the hybrid, so enumeration and then extending to higher degrees, but also some conflict search. And here it is interesting, well, the way that we see the conflict search is different than with SAT solvers. Here what you do is you try to find out whether one is in your ideal. This shows inconsistencies because if you have one in your ideal, it means you have an equation that should be 1 equals 0, right? And this shouldn't happen. So this is how you discover the conflicts. So that's what bool solve does. It enumerates up until some point where, depending on the best trade-off, and then it tries to find some conflict. If it doesn't, if it finds a conflict, you backtrack, right, in the enumeration. If it doesn't, you continue and you compute Grosvenor basis. F4, F5, they're just computing Grosvenor basis. That's everything that they do. And the crossbred does all of this. It does not compute a Grosvenor basis because usually the best trade-offs are where you go, as I said, up to degree 4. It wouldn't go higher than degree 4. So the way that you solve it is by these other techniques, candidate solutions, and so on. Okay, so that was the summary of the solvers. Before I go to the second part, do you have any questions on how we solve things? No? Okay. We can take a small breather, a minute, so that if you have something to write down. Okay, maybe we can continue. So all of the solvers that I told you about today, I said it is kind of like a survey, but it covers everything that is in overdetermined systems, okay? So when you have at least as many equations as variables. What I didn't cover is probabilistic algorithms, Lokshtanov, which, so not implemented, or algorithms for underdetermined systems. And here, actually, because I will look at UOV, we will look at underdetermined systems, but this is not like a big change. I will tell you what we're going to do, okay? And I mean, I will tell you something, an easier trick, and then the actual algorithms are not that different than that. Okay, so in the beginning, we explained algebraic cryptanalysis, that it starts with modelization, and then it goes into the solving part, and then you get the solution. So I talked already about how we do the solving part. I didn't talk about the modelization. How do you describe how do you describe a cryptographic attack as a polynomial system of equations, okay? And here I'm gonna give you examples of applied to U of V, which is what we saw this morning. Very briefly, if, in case some of you weren't there. So this was the trapdoor construction that we're working with, right? So you have this, this is a signature scheme, right? U of V is based on this trapdoor construction. So we had we had this, the private key was this central map F that was easy to invert, right? Because it had a specific structure, and you saw the structure of U of V. And then you obfuscate it somehow by applying a linear transformation on the input on one hand. Also, you can apply a linear transformation on the output. We said in U of V we don't do that because there is no point. And then you get an equivalent, an isomorphic system, okay, which is this public map P here, right? And we said that because these are, these are invertible matrices, you have, or this is an isomorphism, you have a one-to-one correspondence between the solutions of this F and the solutions of this P, right? So if you are, and the way that signing works is that you know both the central map and the corresponding linear transformation. So that means that you can find solutions for this public map P. And it started with this diagram that I showed you, right? You had this, you first hash your message with some salt probably, and you get your target vector. So this is this W, this is the thing that you want to, this is the vector that you want to find the pre-image of, right? So in order to do that, first you did the inverse transformation on the output, right? You went through the diagram in the other way. And then you invert the central map that was easy to invert, and then you also do the inverse of the transformation on the input, and you get this Z, right? And then you send this Z as a signature, and then alongside your message, right? And then on the other side, the verifier, or Bob here, can recompute this target W, right? Because he takes your message, or also the salt if you sent it, or if you have a deterministic way of determining the salt. And then Bob checks exactly whether this Z that you sent is indeed a solution to the system, meaning if you evaluate this public map P in Z, then you will get this exactly this omega that you were supposed to get. So it means that Alice has this information because she was able to solve it. Okay, so this is the system that we're going to attack. And as an example, we gave U of V, right? And we saw what the U of V central map looks like in matrix form, which showed you immediately why we don't do the transformation on the output, right? We said any linear combination of these matrices will also give us a matrix that looks like this. So it doesn't make sense. Okay, so this is what we're going to focus on. And I'm going to tell you about 4 different attacks. It's mostly about so that you get an intuition of how modelization works and how important it is actually for the attack, right? Because not just the solving part, but the way that you model the problem is, in most cases, in most structured cases, it is the crucial part. Okay, so I'm going to go through the direct attack, which is a forgery attack, and then the other 3 are key recovery attacks. Okay, so the direct attack first. As the name suggests, we are going to try to forge a signature only using the public key. So directly you try to solve this public map, right? We said that this is a hard problem. It should be still hard, even though it is isomorphic to a system that has a lot of structure. You can try to attack the problem directly, meaning you're trying to solve the MQ problem. So you're just using the solvers that we had directly. Okay, so what does this look like? What is the constraint? For all of these attacks, I'm going to tell you this is the constraint that you're modeling, and this is what your system looks like. What is the constraint that you're modeling? You're given a target vector W, right? And then you need to find a Z such that P evaluated in Z is equal to W, okay? And I'm going to model this in matrix form, right? Because now you're used to seeing the matrix representation of the polynomials. So these are the equations, right? For each polynomial, and this is, let's say P to the 1 is the matrix representing P1, the polynomial. So we saw this morning how you evaluate polynomials in matrix form, right? You multiply with the vector on one side and then on the other side. So you need to find a solution to this system here. Okay, that is for each. So that you can think about what is the number of variables and what is the number of equations, which is always like the starting point. It is the most important thing that you're gonna look at for your system. I'm gonna enumerate, I'm gonna put them in color here. So yeah, you have everything that is in blue is kind of this, it contains constant terms in the matrix, and everything that is in red, it contains the variables, the unknowns of your system, right? I didn't have the slide where I show what modelization looks like. Do you imagine what, how I go from here to a system of equations? So let's say you fill them up, right? These vectors, these z vectors, you fill them up with variables, z1, z2, z up until, yeah, zn. And this matrix, you fill it up with the coefficients, right? And then you multiply. And so when you multiply this, you will get let's say only a matrix of 1 by 1, only one entry, and that will contain like a linear combination of variables. Okay, that is how we model matrices. So in this case, then what is the number of variables? Depends on the length of z, right? It is the number of variables, a number of entries that you have in z. Okay, so in our case, we said U of v, it has n variables, meaning v vinegar variables plus o oil variables, which is about 2 times 5 the number of equations that you have. Okay, so here the number of variables that we have is n, and the number of equations is what? 1 per row that I have here. Okay, so it is here in this case m equations. So we are faced with a underdetermined system, right? What we're going to do here is, well, there are also, as I said, some specific algorithms, but basically what you can do is, if you know that you expect more solutions now, and we do, right, because you have a lot more variables than you have equations. So we expect to have more solutions, and we also expect to have about one solution when we have the same number of variables and equations, okay? So you can not enumerate this time, you can just fix variables until you get to, so you can fix all n minus m variables, right? And then you still expect to have one solution, or you won't have it, but then you try again and you try again, and this, yeah, you try it about q times at most, and it should be, it should work out. Okay, so let's say that is how you solve the system. Once you do this enumeration, then you go into the solvers that we talked about, okay? That is how we're going to solve underdetermined systems now. Okay, so that is the direct attack. It just finds you a pre-image directly. Well, not very efficient, right? You have to go directly to the solvers. Okay, then the reconciliation attack. This one is trying to find instead a secret key. So the rest of what I'm going to talk about is going to be about finding the secret key. And I do have to tell you some more notions around that. So, for instance, I need to tell you about the secret subspace O, so the secret oil space, right? And you might have heard about this, not just in cryptanalysis, but now we also use it for the description of the scheme and for signing and so on, because it is more convenient. Okay, so we say that this public map P that we looked at, the public map of U of V, it has a trapdoor, right? Why do we say it has a trapdoor? Well, it vanishes on a linear subspace of a pretty high dimension, as high as the number of equations. So this is very untypical, right? It doesn't make sense that your variety should look like this, that it should have a linear subspace in it. But this one does because of the trapdoor. So that means that for any vector in this subspace, O, right, this P evaluates to 0. Okay. Why do we have this? It is easier to look at the central map than the public map, right? Because the public map is pretty, yeah, it should be a bit indistinguishable, so it should look a bit random. But I can explain to you, looking at the central map, right? If you think about the central map, this is what we had. We had this matrix in the middle. This is what the F1, F2, etc. look like. Okay. So let's look at this m-dimensional space. Let's look at the space where if we take all vectors of length n, and we set the first n minus m entries to 0, exactly, and then the rest is whatever. Then actually all vectors that look like this, the central map vanishes on all of them. And it is, you can see it from the image. Do you see it from the image, or do you want us to to write it out. So if you look at this in block matrix form, right, let's say here you have the V variables, here you have the O, so you multiply this by this, and then when you multiply on the other side, you will see that in all of the terms that you get, yeah, I couldn't connect my writing thing. All of the terms that you get will involve vinegar variables, right? Will involve some portion of this block of the matrix if you multiply this. And here it is all 0, so everything will be 0. So that is the subspace that over which P vanishes, okay? So, and what is the dimension of that subspace? How did I describe it? So you have some fixed variables in the beginning of your vector, and then you have m free variables, okay? So it is an m-dimensional linear subspace. Okay, and then we also said, so I convinced you that this central map vanishes on this linear subspace, right? So then we also said that we, between the central map and the public map, we have this isomorphism, so a one-to-one correspondence between the solutions. So that means that I also, all of these solutions of this central map that are in this oil space, they also appear in a linear space in the public map. And you can find them easily, actually, if you know the linear transformation between the two. This is what the oil space looks like on the side of the public map, right? If you take this space that we described here, this O prime, and you multiply it with the inverse of your linear transformation, then any vector that you take here, if you multiply it by S inverse, then you get into a vector in the oil space. Okay. And so that is the one that we're going to denote with this O, and this is, your public map P vanishes on this O, because your central map F vanishes on O prime, right? Okay, so that is the big takeaway of the oil space. Now for the reconciliation attack, what does it do? Well, it wants to find the secret oil subspace. Because if you have the disruptor, the secret space, then you can sign everything with it. And actually, this is how you sign. This is how you sign now with the newest, let's say, the submission to the NIST. That is the traditional UOV. That was the first time they used it in practice. You sign using the oil space instead of going through this classical way of looking at things that I told you about. Okay, so what does it mean to find this subspace? It means to find a description of this space, right? So basically a basis, right? So I need to find m linearly independent vectors that are in this space. So that is what we're going to try to model here. Okay, so what are the constraints? There is another thing part of theory that I need to tell you about, and this is the second to last one. So you have this polar form for polynomials. What is a polar form for quadratic maps specifically here? The polar form of a quadratic map is this bilinear form that is defined exactly like this. So if you evaluate the polar form in two inputs x and y, it is the same thing as if you evaluated the corresponding quadratic map in x plus y and then minus the quadratic map evaluated in x minus the quadratic map evaluated in y. Okay, so that is just the description of the polar form. What does this look like? What does this polynomial look like? Well, if you try to write it out, and let's say now I'm going to use what we call the upper triangular representation of polynomials. It's kind of the same as the symmetric one that I showed you, but you only have coefficients in the upper part and they are not over 2. Okay, so what is this? By definition, if you take P prime in x and y, by definition, I can rewrite it like this using the quadratic map. And then, that is what I did up until here. And I still cannot, write anything. Then I put it in matrix form, right? What does this look like in matrix form? Evaluating the P in x plus y is like multiplying x plus y times P and then times x plus y on the other side, right? What we saw with the matrix representation, and here minus, same thing with x and same thing with y. So if you redistribute, if you rewrite this, some things cancel out. This is what you get here, right? X times P times y plus the other way around, so y times P times x. And if you take the transpose of this, this is what you obtain. So here you have X times some matrix here in the middle, right, times the Y. And this matrix here, I'm going to call it B. And what we know about this one, and well, I'm going to call it B, and I'm going to rewrite this like this here, okay? What you see here, right, I don't know if you see my mouse. Yeah, I'm pointing at this one. What you see here, it should remind you of this representation that I had for bilinear forms this morning, right? You can also represent bilinear forms as a matrix, and there we said that if you, this is going to be some matrix that such that if you multiply x times this times y, you get this bilinear monomial, okay? So what we know about this map is that it is P prime, it is bilinear, and also it is symmetric, right? Because I took something plus, I took a matrix P plus its transpose, so it is also symmetric, okay? These are the two things that we know. We also know that it vanishes on the oil space. Okay, I'll come back to that later. So now we can do the reconciliation attack. What are the constraints that I want to model? As we said, I want to find the oil space, find some vectors in the oil space, right? So I will model things that I know about vectors in the oil space. First thing that I know is that all of the monomials, all of the polynomials in my quadratic map evaluate to 0. On the oil space, right? So if you have some vector OI, let's say here, in the oil space, you have that OI times P times OI is equal to 0, okay? That is one thing that I know, and I know this for all polynomials, let's say. And then I also know the second thing because of what I told you before, but we are going to repeat it. So that any pair of vectors that are vectors from the oil space, we also have that the polar form vanishes on, when evaluated to these two vectors. Why is this the case? This is really for oil vectors, and it's not trivial. It's because of the linearity of the trapdoor that you have. So here, if I substitute it now, so if it's an oil vector, we know that, it is a solution, okay? So we know that we have P k of x is equal to 0 for any, for every polynomial. You also have P of y is equal to 0, but because of the linear property of the space, you also have that P of x plus y is also equal to 0. So this whole polar form is equal to 0. Okay, this is what you get from the linearity of this trapdoor. Okay, so now I also know the second constraint here, that OI for some one oil vector times B times OJ is also equal to 0, and I'm going to model this for, I'm going to show you a loop. Actually, we do everything at the same time. It's not really a loop, but let's say modelization is a loop. Okay, so what are you doing? You are trying to find a basis of an m-dimensional space. Okay, so it means that for the first vector that I'm looking at, I can just set everything except for m variables, right? I can keep no, the other way around. I can keep these variables, and the rest of it, the m here, I'm going to set them first at 1, 0, 0, 0. Then for the second vector that I'm looking for, I'm going to set them to 0, 1, 0, 0, 0, just so that I get like an independent vectors, that I get an actual basis. That doesn't matter so much. And I'm modeling these two constraints for each oil vector that I'm looking for. So if you look at this, what does it give you as equations? Now you're more used to seeing systems like this and figuring out what you will get. So here, in this first one, you get a bilinear system, right? Because I have variables in OI times some constants times some variables in OJ. So this one gives you a bilinear equations from the two oil vectors that you're looking for. This second one gives you just a quadratic system, OI times P times OI. Let us imagine first that we are solving this iteratively, one by one. So let's say in this part of the loop, you can solve, if you try to solve the system, then you might as well just solve the second one first, and you get one oil vector, and then when you plug it in the next one, you will get a linear equation, so then it becomes a bit easier. So that is a bit the takeaway, that the bottleneck here is solving for the first oil vector, right? And once you have one oil vector, then you have a lot of linear equations. And linear equations help immensely with your resolution, right? Because if you have, every time you have a linear equation, it's basically one free variable. You can remove it from your system, you can do Gaussian elimination, you can take it as a pivot, and you can substitute what you get on the other side in your system. It's basically like you lost one equation, and you sacrificed you lost one variable, and you sacrificed one equation for it. Okay, so every time that we can find linear constraints for anything, that is very good. So the bottleneck of this is solving actually this big part. You're not going to do this iteratively just because, if you don't model everything at the same time, you will get other solutions of other linear subspaces that are not exactly the oil space, but that is like a technical detail. And so this is the reconciliation attack. You model this and you obtain the whole basis of your oil space. And as I said, once you have the oil space, you can sign and you can do everything. And concretely, these are the, as I said, these are the unknowns and the constants in the system. Okay, now to tell you a bit of a more involved attack, or to arrive to the last one, that is kind of the state of the art for how we choose parameters for U of V. I do need to tell you about a historical attack, which the Kipnis-Shamir attack. This one is not on U of V, this is on OV only, so the balanced oil and vinegar. When it first appeared, what does this balanced and unbalanced refer to? When oil and vinegar first appeared, it used to be the case that, I told you have to have as many equations as oil variables, so that when you enumerate, you get a square system, right? So what they chose is that they had twice as many variables as equations, okay? The number of vinegar and oil variables was equal. Just, maybe a convenient choice for constructions, but it turns out that this really killed the system when it came out, because if you don't have this, if you have the same number of vinegar and oil variables, you can attack the system very easily, polynomial time, and we will see now why. This brings me to the last thing that I have to, let's say, tell you about, and that is what is the orthogonal complement of a subspace, because we're going to use it in the Kipnis-Shamir attack. So let's say you have V, which is a subspace of FQ to the N. And then we say that its orthogonal complement is this V perk, such that, if you take a vector from your subspace and you take another vector from its orthogonal complement, if you do the dot product, it's going to be equal to 0. That is what it means to be in this, or we call it a dual space in coding theory, and it might come up tomorrow, I don't know. Okay, so what do we know about this orthogonal sub-complement? We also know something about its dimension. This is the only thing I need for the attack. So you know that if the dimension of V, your subspace, is M, then the dimension of its orthogonal complement is going to be N minus M. Okay. So what happens now in the Kipnis-Shamir attack? Again, the goal was to find the secret oil space, and this is how they did it. So first, they observed this, the following constraint that just gives you everything, actually. So you know that for each matrix in your polar form, okay, so this is the bilinear one that we talked about, you know that each matrix, a matrix of your polar form sends this oil space into a subspace of its orthogonal complement. Okay, so there's no easy way to say this except for giving you a proof, right? There's at least I haven't found an intuition. So if you want to prove this, you say, okay, let's take a vector in the oil space. So that is, let's say, this O2 here, and then if I take a vector in this thing B times this space B times O, right? So that is going to be this matrix B times O1, something that is an oil vector. If I take the dot product between them, what happens? You get exactly this thing here, O2 times B times O1. And then this looks a lot like a polar form. It is exactly, it is the polar form. So it means like if you're evaluating P prime in O1 and O2, and if I rewrite it by the definition that I gave you of the polar form, that is equal to P of O1 plus O2 minus P of O1 minus P of O2, and we said that this is 0, right? Again, because this one is 0, you know that about the oil space, This one is also 0, but also the sum of it, the P vanishes also on O1 plus O2 because of the linearity that we have. We are really in the oil space. We are not only at pre-images of 0. Okay, so we have proved that this actually, this second vector that I have here belongs, well, it is in the orthogonal space of this O. So it means that, yeah, this thing here is a subspace of it. Okay, so now that I know this, I have constraints I can model, right? This is very interesting algebraically. There is something more that I know. It's not just that it is a subspace. If you look at the dimensions and what we said about the dimension, we know what is the dimension of this so this orthogonal complement of O. It is exactly n minus m, and here n was what? Because we're in the balance case in the original submission, right? So it is n is equal to 2 times m. So the dimension of its orthogonal complement is also equal to m. So it means that we don't just have a subspace, we have equality. It is the same subspace. Okay, so now I can model stuff. And also this is true not just, okay, here I said bk, right? But this is true for all matrices in your polar form. And so that means that you have b to the k1 times the oil space is equal to another b to the k2 times the oil space. This is what I'm going to model, that these two are equal, right? So I put, and this O, imagine it, yeah, as just a basis of the space. So I put this b to the k1 on the other side, right? So I get a b to the k1 inverse times b to the k2 times the oil space equal to the oil space, and this is for all pairs of matrices b, k1, k2. How many do you have? We have m of them, right? So pairs, it's m choose 2, right? So this is a lot. There's a lot to model, and it turns out that, yeah, it is a polynomial attack because finding a common invariant subspace of a large number of linear maps, it's easy. I don't even think they do it algebraically in the original one. It's just, it's a polynomial algorithm. Okay, so that's why the initial proposal of oil and vinegar was attacked. And this does have some generalization. So you can, there are subsequent works that generalize this attack. But mostly, yeah, so it means instead of looking at, we won't have equality here when, yeah, then they set n to be bigger than 2 times m, right? So you don't have equality here anymore. You still have this thing. This is something that we proved in the beginning. You have that it is a subset. So you can look for vectors in the intersection, but yeah, very quickly this becomes very exponential. So yeah, it is not a very efficient attack on U of V anymore. And then, yeah, oil and vinegar became unbalanced oil and vinegar. And now this brings me, I have all the intuition that you need for this last attack, the intersection attack by Boolens in 2021. So, yeah, and it's not the weekend on a laptop on Rainbow, but it did bring a lot, it's even more interesting to read, I think, than that one. It has, all of the techniques are in this one. So, again, it's like we use the ideas from the Kipnis-Shamir attack, but for the unbalanced case, okay? So, and again, the goal is to find the oil subspace, so it is again a Q recovery attack. Okay, what are we gonna do? So now, as I said before, since n is bigger than 2 times m, then the dimension of the orthogonal space of this O is, complement of this O is going to be bigger than m also, okay? So we still have that B times O is a subset, is a subspace of this. And yeah, we have all of the constraints, but it's only a subspace, and it is not, we don't have equality. They're not necessarily the same subspace, okay? So you can still try, what we're going to do here is we're going to try to find vectors in the intersection of these two. Let's assume that the intersection of these two is not trivial. And then we're going to try to find the vector in this intersection. This is a pretty valid assumption, but here that I took only two subspaces, so that I took the intersection of only 2 subspaces. And with the parameters of U of V, it is a pretty valid assumption, right? So yeah, let's say we have there exists a vector X in this intersection, and we're gonna look for it, okay? So what do we know about this vector x? Okay, so remember this is now not an oil vector. It is in when you have already sent the oil space there, so it is going to be a vector in this intersection. Okay, so if x is in the intersection, then we have both, by definition, it means that this vector x was obtained from an oil vector by applying this transformation that is described with the B matrix, okay? So it means that B to the K1 inverse times x is an oil vector, right? And same with this B to the K2 inverse x, it is also an oil vector, okay? And we saw in the previous attacks, we know how to model the fact that something is an oil vector, right? We had two types of constraints. We know that the quadratic map vanishes on those kind of vectors, on the oil vectors, and we also know that the polar map vanishes on on a pair of oil vectors, okay? So these are the three things that I'm gonna model. Exactly, this first one says that B to the K1 inverse times x is 0, right? Because it's an oil vector. This also, it says that the second one is also an oil vector, and that this one models the, let's say, the fact that the polar form also vanishes on a pair of those. Okay, so that is the entire, I mean, those are the constraints of the attack. And then you can, I showed it here with only two, an intersection of two. You can generalize this, right? You can also try to find a vector in the intersection between three subspaces, right? Because you have several matrices, B, K1 to Km that you can choose from. What is the catch, right? What brings the trade-off here? On the one hand, if you look at let's say an intersection between three subspaces now. The positive is that you will get what? You will get a lot more equations, right? You have these three equations, you will get another, well, 3 times, you know, however many this gives you, this 3 packet of equations, let's say. You will also get these 3 packets from, let's say, the second with the third vector, the second with the third space, and you also get another 3 from the first with the third one. So you get all of these combinations. You get 3 times as many equations, so that is good, right? That means you can solve better. However, on the other hand, here we made the assumption that this intersection here is non-trivial. And this kind of, it's a good assumption when you have an intersection between two, but once you start getting more and more, so then at some point it will become, there won't be any vectors in the intersection. That's what's stopping you from doing this attack with as many matrices as you want. And I think that for U of V parameters, the best trade-off choice is 3. You're looking for a vector in the intersection of 3 subspaces. Okay, so that was everything for today. So what we saw that, first we saw how hard the MQ problem is. Well, usually it is hard. Of course, there exist easy instances. We have a variety of solvers for overdetermined systems, and these are really, I can't stress enough that this is for generic systems, and the complexity is really known for generic systems. Usually, cryptographic attacks give you structured systems, and you need to analyze per case, right? You need to analyze both, analyze the complexity of the solvers or find some better tricks. There are better ways that you can solve the systems if you know what the structure is. Modelization, on the other hand, can be crucial to how efficient an attack is, right? We saw that, we went from a direct attack that was very inefficient up until this last attack that was, the most efficient modelization of the 3 that we saw. I'm not considering Kipnis-Shamir there because it's not really an algebraic attack. So as we said, the MQ problem can be easy for some structured systems, and this we use as a trapdoor in multivariate cryptography. When we are working on the trapdoor side, right, I told you there's also other multivariate signatures that are based on a Fiat-Shamir provable construction, but that is a different thing. And then we saw 3 ways to model this U of V trapdoor, and that was everything. So I can take your questions now.